Hey everyone, and welcome. So, what happens when a bunch of math lovers get together and try to solve a problem about, of all things, hyperspace? Well, you get a story full of amazing patterns, late-night breakthroughs, and a fantastic journey of discovery. Today, we're diving into a really cool article by Kate Nowak to unravel a mathematical mystery that starts simple and ends up somewhere way beyond our imagination.
Okay, let's just jump right in with a question that honestly sounds impossible. How in the world do you count the edges of something you can't even see or build? Well, this is the exact challenge a group from the Math Circle Summer Institute decided to take on. And trust me, their journey is fascinating. Right, so to even begin to get a handle on the fourth dimension, you can't just leap into it. You have to build your way up. The group started smart by grounding themselves in the dimensions we all know, the ones we can actually see and touch. The core idea here is actually surprisingly simple. You can think of it like this. You generate a new dimension by taking an object and just pulling it in a new direction, a direction that's at a right angle to all the others. So a zero-dimensional point, you pull it and poof, you get a one-dimensional line. You take that line and pull it sideways, now you have a two-dimensional square. You take that square and pull it upwards, and there it is, our good old three-dimensional cube. To really make this click, the group came up with some pretty great analogies. Imagine a 1D line is like a tiny monorail track. You can only go forwards or backwards. A 2D square, well, that's like upgrading to a car. Now you can move forward, back, left, and right. See? Each new dimension just adds another way to move. So, with that framework, the group started counting. They made this their clue board, a table to keep track of the boundaries for each shape. You know, a line has 2 vertices, a square has 4 vertices and 4 edges. A cube has 8 vertices, 12 edges, and 6 faces. This table right here, this is the start of the whole investigation. These are the first clues to the mystery. This step-by-step process was all well and good, up to a point. But it was about to run into its biggest challenge yet, trying to use that same logic for a dimension that we literally cannot perceive. So this is a tesseract, or a hypercube, but it's not a real 4D object. The best way to think about it is as a 3D shadow of a 4D object. Kind of like how your shadow on a wall is a flat 2D projection of your 3D self, this is a 3D projection of a 4D cube. It's really the closest our brains can get to picturing the real thing. And this quote from Kate Nowak just nails the problem. She writes that the group hit an intuitive wall, because you can't actually pull a cube into a fourth dimension in our world. That simple method that works so well just stopped. And it forced them to rely on pure logic and pattern finding instead of something they could see. So what do you do when your intuition fails? You get creative. Using an origami cube, some coffee stirrers, and a plastic box, basically stuff they found around the office, they built this model. Now, it's not a real tesseract, obviously, but it was a physical representation of that 3D shadow. And that was just enough to help them wrap their heads around the problem and actually start counting the boundaries. Okay, so armed with their clever model and their step-by-step logic, the team could finally fill out their data table. And this is where the real detective work began, hunting for hidden patterns buried inside the numbers themselves. And here it is, the completed clue board, now with that hard-won data for the tesseract. I mean, just getting this single row, 16 vertices, 32 edges, and so on, was a huge achievement. But then the group did something else, something really important. They added one more column, where they just summed up all the boundaries for each shape. And that's when the magic really started to happen. The first major breakthrough came from that new sum column. For the line, it's 2 plus 1, which is 3. For the square, it's 4 plus 4 plus 1, which is 9. For the cube, 8 plus 12 plus 6 plus 1, that's 27. Are you seeing it? 3 to the first power, 3 to the second power, 3 to the third power. The total number of boundaries was always a power of 3. So the huge question was, would the pattern hold for the tesseract? They had done all that hard work to count its boundaries, they added them up, 16, 32, 24, 8, and 1, and they got this number. 81, which is exactly 3 to the power of 4. Yes, the pattern held. Nowak called this a gratifying result, and you can see why. It was the first solid proof that their logical jump into the fourth dimension was on the right track. Then they found something even deeper, a rule that could generate any number in the table just by looking at the row above it. Now, I know the rule on the screen looks a little intimidating, but stick with me, the idea is brilliant. Let's say we want to find the number of edges in a cube. The rule says to look at the row above it, the squares row. You take 2 times the number of edges on the square, so 2 times 4 is 8. Then you add the number from the column to the left, which is the number of vertices on the square, or 4. 8 plus 4 is 12. And there you have it, 12 edges on a cube. It worked for every single number on the chart. So they had found these incredibly powerful patterns. But the team was exhausted. It was almost midnight. And while their rules worked, there wasn't one single beautiful picture that tied it all together. They decided to call it a night. But as it turns out, a fresh pair of eyes was about to see the data in a whole new light. The next morning, a member of the group named Rudy had a total eureka moment. He said the table reminded him of the famous Pascal's triangle. So he just tried something simple. He took their data and just staggered each row. And there it was. On the right, you've got Pascal's triangle. And on the left, their data perfectly arranged into what they instantly called Rudy's triangle. It's incredible. And this new triangle had its own simple, beautiful rule. It's almost like Pascal's triangle, but with a little twist. Instead of just adding the 2 numbers directly above, you take 2 times the number above and to the right and add the number that's above and to the left. Let's take that 32 in the bottom row. It's just 2 times 12 plus 8. It's simple, it's powerful, and it works for the whole thing. And here it is, the grand finale, the final piece of the puzzle. It turns out Rudy's triangle isn't just some neat pattern. It's the exact pattern of coefficients you get when you do the binomial expansion of 2x plus y to the nth power. This explains everything. It even explains why the rows add up to powers of 3. If you just pretend x and y are both 1, you just get 2 plus 1 to the nth, which is 3n. A perfect, elegant connection tying it all together. But this story doesn't just end there. Because, as it turns out, this group wasn't actually the first to discover this pattern. And when their article was published in the Mathematics Teacher Journal, it started a whole new conversation, which highlights something really cool. Discovery is so often a shared human experience. So after the article came out, 2 other mathematicians, Dean Priest and Steve Smith, wrote in. Turns out they had discovered Rudy's triangle years earlier while doing similar research. But they weren't trying to stake a claim or anything. They were just celebrating, praising Nowak's article for perfectly capturing the pure joy of mathematical investigation. And get this, they offered a completely different way to visualize the same numbers. Instead of counting the boundaries of hypercubes, you could think of it as counting dots in a hyperwindow. A 1D line has 3 dots. A 2D window has 9 dots. A 3D arrangement has 27. It gives you the exact same pattern, 3 to the power of n, but through a totally different geometric lens. It's a beautiful reminder that there's often more than one path to the same truth. And that really brings us back to the heart of this whole story. As Kate Nowak says, it didn't really matter that others had made these discoveries before. What mattered was that it was new to them. They had a fascinating problem, they had the time to work on it, and they had the collaborative spirit to see it through. It was, in her words, a perfect learning storm. And that's what makes this so powerful. It ends not with a period, but with an invitation. The final question in the source material leaves us wondering, what if we changed the rules for Rudy's triangle? Instead of multiplying by 2, what if we used 3 or 4? What new shapes, what new mathematical truths are just out there, waiting for the next curious person to come along and find them?